What's going on, everybody? This is Mr. Diamond, and this is the second set of notes for Chapter 6 of General Chemistry. We're talking about chemistry calculations. The last video, we talked about scientific notation, and now we're going to talk about something a little more complex. That was kind of a softball to make it a little easy on you at the very beginning here, but we're gonna move into some tougher territory. So we're going to start by talking about measured numbers. When you measure numbers using a tool, you are expected to actually use your skills as a scientist to make an extra level of prediction beyond what you can actually see. And this is important for science because it's not like in math class where like a lot of the numbers get made up or you pull them from some other outside source or you get it from data from people. We get a lot of our measurements and our data in science from tools. So when you measure something, let's say for this graduated cylinder, you probably already kind of do this in your head, but this is actually valid and is a required scientific practice. So when you look at this, you would go, okay, this line here is about a 50. If I check here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines between them. So every line would be a 1 going from 50 to 60. So I would go 50, 51, 52. And then in case you haven't looked at a graduated cylinder in a long time or you forgot the rules, remember we don't measure from the top here. We measure from the meniscus, which is this bottom piece right here on a graduated cylinder. So we would go 51, 52, but then we get into, well, it's between 52 and 53 here. Now, I know most of you are probably like, well, that's not how I would think of it. I would just go, well, it's, and you would say a number. But I'm kind of talking through the process we would actually be using in science. Normally, if we were just measuring it, some people may think, well, I can't accurately say what it is, so I'd have to say I guess it's closer to 53. But no, you wouldn't actually do that to be scientifically accurate. What I assume most of you did was you went, okay, 51, 52. It's almost 53, but not quite, so I'll call that like 52.9, 52.8, somewhere in there. And even though you might be thinking, well, that sounds kind of like guesswork, it is, but we are expected that if you're doing science that you have enough capability to guess slightly further than what your devices can actually read. You can detect that minor change. So the lines are placed so that way we can actually report our answer, even though it's only to 1 milliliter units, we can report it to 0.1 milliliter units. So instead of 53, we would say 52.9, even though there's no actual line saying a 0.9 on that thing. It's just as scientists, we are okay with reporting one digit further. Now, if you would try to report even further than that, like if you would say like 52.99, that would be incorrect. Now you're going a little bit too far to really accurately be able to make that guess. But you are given the freedom to make one extra digit than what your device can actually measure of a guess whenever you're reporting a value. Now, because of that reason, we have a system to determine how good or bad our measurements are, and that is significant figures. Because so many values are taken by a person looking at something instead of like a machine just popping out an answer, we have to base our answer on how good the measurements are. So to do this, we have to determine which values or which digits in our number are significant, are relevant to our actual calculation. So because of this system, you're actually never going to have to ask, well, what place do I round my answer to in this class? The answer is the values will tell you. The question should tell you what number you need to round your answer to. So significant figures or significant digits, or I'll usually abbreviate it Sigfigs, are all of the necessary digits plus one estimated digit from measurement. So if we go back to this number here, this 52.9, those are our significant digits or significant figures. All three of them are significant. We measured the first two, we could accurately see the 52, and then the 0.9 was one step beyond that. There are rules that actually govern what digits are necessary when you look at a number. You have to have these memorized, and these are used in basically every science class where you'll eventually do math problems. So physics, chemistry, advanced biology classes, all of them will eventually get to the point where you will need sig figs. And if you take any classes with me in the future, you are going to have to use sig figs. So how do they work? Here's the basic sig fig rules. Everything that's not a zero is significant. Zeros are the only thing that's up in the air. Zeros can be significant or not significant depending on their context. Now, obviously, that rule right there is just not good enough. Like that doesn't help. So we need to get a little bit more specific than just saying all of the non-zeros are sometimes. So here is our actual breakdown for our rules. A digit is significant if it is not 0. It can be significant if it's a 0 between two significant digits. So for example, 1001, those are two zeros, but they are between two ones. Because they're between two significant digits, they are themselves significant. If it is a 0 or multiple zeros placed at the end of a decimal number, it has to be at a decimal number. In fact, I'm going to really quick go in here and I'm going to underline and bold that because it is very, very, very important that it is a decimal number. So while 1,000 only actually has one sig fig, the one at the beginning is not a 0. The zeros haven't fallen into our criteria yet, so those zeros would actually be insignificant. 0.200, those zeros are at the end of a number and after the decimal, so they would actually be significant. These zeros are at the end of the number, but not after a decimal, so they would not be significant. The reason for this is because in 1,000, we don't actually know what kind of tool we were using. These zeros here, we aren't given enough information as to whether or not they are significant. The tool we measured may only measure in thousands. It measures like 1,000, 2,000, 3,000, 4,000, 5,000. And we don't know that. So those zeros are really only there to tell you the number is bigger, which is kind of like an abstract way to think about numbers. We don't normally think about it. But when you have like 1,000, the only thing these zeros are telling you is that this 1 is actually not a 1. It is 3 zeros worth bigger, or it is 1,000 times larger than a 1. But in this case, you're not just saying, oh, well, it's like 0.2. You are saying, I have measured this unit. I have measured this device, or with my tool or my device or whatever I'm using. I have measured down 3 decimal places. And in this spot here, I got a 2. And in those spots, I got a 0. Those last 2 zeros are not placed there just to make the number look better. They are placed there because your device read as a 0. It would be like if you measured on that graduated cylinder and it was exactly on 52. You would actually be able to report that as 52.0. No deviation, exactly 52. In this case, this could be a device that measured down to the 0.00, and you said, okay, it says 0.20. It is exactly 0.20, so I'm going to add my extra 0 digit, 0.200. All of those digits are relevant because they're not placeholders. They are showing how good your measurement was. And then finally, if it is written as the coefficient of a number in scientific notation. So every single number that comes before times 10 to the whatever is always significant. So if you wrote 1.000 times 10 to the 0th, or times 10 to the 3rd, all of those zeros would then become significant. But if you didn't put them, if you just did 1 times 10 to the 3rd, that would only be 1 sig fig. Anything you write at the beginning of a scientific notation number is always significant, and that's what you use anytime you have a number with a whole lot of zeros, but not all of them are significant. It allows you to pick and choose which zeros are significant. Now, I don't know if it's on the next slide. Okay, it is. A 0 is not considered significant if it is at the beginning of a decimal number. So in this case right here, let's say we had 0.00034. Now, at the end of a decimal number, we said you added those because they were measures of how precise your tool was measuring for you, and you detected that those numbers were 0. Just like when we were talking with 1,000 a second ago, these zeros at the beginning aren't really there to show you what the number is. They are just placeholders. And you can kind of, again, just like with the example back here, you could prove to yourself by writing it in scientific notation. If you wrote this number in scientific notation, none of these zeros would be there. They are not actually showing you a degree of measurement. They aren't actually showing you how precise you are. Your tool may have only started at this number. We can't accurately say these things attributed to the number we got, only these last 2 digits did. So only those last 2 digits there, only those 2 that aren't zeros are significant. These are all placeholders. And then finally, if it is used as a placeholder in a large number that doesn't have a decimal. Now, this is probably the weirdest rule. So like I said a second ago, 1,000 only has 1 sig fig because that 1 is significant, but those zeros are only placeholders. But if you add a decimal to it, which normally feels very wrong, if you did 1,000 decimal, that decimal is telling you the last part wasn't like 1,000. I didn't say, oh yeah, there's like $1,000 in my bank account, or oh yeah, it's like 1,000 degrees Fahrenheit, something like that. By putting a decimal there, you are scientifically saying, oh no, it is not like 1,000. My measurement was exactly 1,000. That is what I detected. That is what was achieved in doing this experiment. So it makes the value exact. Instead of 1,000 without a decimal having 1 sig fig, 1,000 with a decimal would have 4 sig figs. All of those zeros would become significant because that decimal was added there. Okay, so we've got a couple of examples that we'll talk about in a second. The final bit is kind of an exception to the rule. It's not really an exception, but it's called exact values. Exact values are treated as having infinite sig figs because they are not measured. Any value that you get that is a constant or comes as a conversion or comes from some sort of thing in the universe, we do not consider that to be a number relevant for sig figs. So an example that's not going to be used in this class is gravity. In physics, we use gravity as having negative 9.8 meters per second squared as acceleration. But technically, that digit expands out very far. It's been calculated more exactly than just 9.8, but we would not consider to use 9.8 as having 2 sig figs because it's a value that is derived from nature. It isn't measured in anywhere. It is a calculated constant that is very, very long and has a whole lot of digits, so we don't count it as having 2 sig figs for our purposes. We count it as having infinite sig figs. Another example would be 1 minute to 60 seconds. 1 and 60 are exact numbers. That doesn't have 1 is 1 sig fig, 60 is 1 sig fig. 1 minute is not, oh, there's 1 minute in 60 seconds. It's not like about 1 minute is about 60 seconds. It is exactly 1 with infinite zeros behind it is exactly 60 seconds with infinite zeros behind it. It is exactly 60 seconds in 1 minute. It is an exact value. So we don't have a number of sig figs for them. Their sig fig value would technically be like a number that we just know. It's also any value that you don't measure. So for example, if I asked you how many cars how many tires a car has, and you say 5, for example, you didn't use a tool to measure that. You just used your perception of the universe around you to determine that there was 5 tires for that car. So you don't need to assign a value of significance to it. It's an exact value. Or if you asked how many students were in the room, you could count that number. It wasn't measured. A tool did not give you that number, so you don't need to assign sig fig values to that number. Okay, also 5 comes from, there's 4 and then the spare in the back, just so we're clear. Okay, so we're going to go through here, and I want to give you a moment to try to determine how many sig figs each of these have. You can pause the video if you want to try to work them out. I'm going to take a sip of my Monster really quick, and then we'll go ahead and get to it. Don't recommend Monster Sunrise, by the way. I've been burning through their supply of 0-calorie Monsters, or I guess 10-calorie Monsters in that case, and not on my list to continue and buy again in the future. All right, starting up here at the top left, we have 700. 7 is obviously significant, and then the zeros afterwards, there is not a decimal at the end. There is not another significant figure at the end, so those zeros will be irrelevant. They are not significant to our calculation. So this would have 1 sig fig. It would just be the 7. Can I draw? Do I have that power? That would be nice, but I don't think I do. Okay, going to the next one. We have 2, 0, 0, 1, 0. The 2 and the 1 are significant, and if you remember, one of the rules was zeros between 2 significant digits are also significant. The way I usually do that is, like it says, kind of underline here. I would underline the 2, underline the 1, and once you've done that, make sure that you connect the lines together. So in this case, if there was a line here and a line here, you would connect them by drawing a line between them, because every digit between those 2 significant digits also is going to have to be significant. So these zeros are for sure, but this 0 at the end here is not between significant digits. It's at the end of a number, but it's not a decimal number. There is no decimal at the end of the number, so we are good. It is just going to be those 4, 2, 0, 0, 1. Again, that digit still needs to be there. Don't think that means that you get to take that digit away. If I ask you to round sig figs, some people start trying to cut off numbers. You can't do that. You still need it as a placeholder, but the ones that matter for our calculation purposes are only going to be these 4. Going to the next one, 3.040, we have 3 and 4. Draw a line between it. That 0 in here is between them, so it's going to have to be significant. Now for this 0 here at the end, it is at the end of a number and it's after a decimal. Because both of those things, this 0, you can't just willy-nilly add them to the end of a decimal number. If it's there for a purpose, and it's there because the detection or the measurement that was taken wants that number to be a 0, which means that is 4 sig figs. Going over here to the next one, 0021 or 2.44. These zeros at the beginning are completely irrelevant. Leading zeros is what we call them. Anytime you get a problem, you should just cross out all of the zeros at the very beginning. They are irrelevant to your sig figs. Not cross out as in ignore them, because, for example, on here you need them, but they never count for sig figs. Until you hit the first thing that isn't 0, none of the zeros in front of that matter. So these zeros, irrelevant. 2 is the first thing that is significant, and then we have 4 and 4. So that is 3 sig figs. Going to the next one, same thing applies. Again, we need these zeros. They are placeholder values. They are there so that way we can determine that this is a small number. We need them to tell us that this number is very small. But they aren't actually contributing to our value. So ignore, 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 ignore. 3, that's a significant digit. It's not 0. And then these zeros are at the end of a number and after the decimal. So that means that they are also significant. So these zeros here are significant. This 3 is significant. That is 5 total sig figs. And again, that means if you wrote this in scientific notation, you would have to write 3.0000 times 10 to the negative 4. 1, 2, 3, 4. Yeah, times 10 to the negative 4. They would still have to be there, but these zeros at the beginning would poof. They would disappear. They wouldn't be in your number. All right, going to the next one, 6.000 times 10 to the 5th. This is actually really easy. The times 10 to the 5th tells us in scientific notation, which tells us every number over here is significant. So all 4 of these are significant. You don't even have to check if they're zeros or not zeros. Every number it tells you at the beginning part has to be significant. Going to the next one, 2.68, same thing. It's times 10 to the negative 2. We don't care about that other than telling us it's scientific notation. It tells us the number is smaller than 1, but all 3 of these digits have to be significant. Okay, going to the next one, 8500 decimal, so 8500 point. It's a weird way to say it. That's usually how I'll say it. So this one has 8 and 5 are both significant. This 0 is at the end of a number, but not after the decimal. But putting a decimal is telling you that this number is not about 8,500. It's telling you it is exactly 8,500. That is the number that was exactly measured. So all of these digits will then have to be significant. These zeros will become significant, totaling 4 sig figs, or significant figures. Okay, going to the next one. First 0, unimportant. You ignore zeros at the very beginning of a number until you hit the first thing that isn't 0. 9 is the first thing that isn't 0. 2 and 3 are also significant, which means this 0 in the middle has to be significant because it's between significant figures. This 0 is at the end of the number and after the decimal, which means it is also significant. That is 5 sig figs. Everything except that first 0 is significant. Then we have 3, 6, 4, 2. All of them are not zeros. 4 sig figs. Pretty easy. And then our last one is a very long number, but as you're going to see here, there's a trick you can do if the number is really, really long. So what you can actually do is just figure out the first digit that's significant and the last digit that's significant. Because like we said, all of the numbers between significant digits also become significant because they are between them. So if we look at this and we go, okay, that 0 is insignificant. That 4 is the first thing that is significant. This 0 at the very end is at the end of a number and after the decimal. That means it is also significant. We can just underline the whole number all the way back to that point. All these 2, 3s, and 1s will be significant. They are all non-zeros. And then all of these zeros are then between significant figures, so they are also significant, meaning 48.02301020 would be all significant digits. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant figures. All right. Hopefully that makes sense. This rule is usually a little bit weird for people at first, and you really need to be able to do this because we're going to talk in the next video about how we apply this to calculations. If you have any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.